So I'm a theoretical physicist, and I work on general relativity, which is Einstein's theory of space, time, and gravity. So this is generally seen as Einstein's greatest achievement. In fact, it's one of the human race's greatest achievements. Furthermore, in 2 months' time, we're going to be celebrating the 100th birthday of general relativity. So I thought this was a good opportunity to tell you something about this theory and explain why it's still very much at the forefront of research today. So, basic idea of the theory is that the concepts that we call space and time are not really distinct things, but instead they're just different aspects of a four-dimensional entity, which is called, unimaginatively, space-time. The next main idea in general relativity is the idea that the phenomenon called gravity is simply the curvature of space-time. So that sounds complicated, so this picture shows you a cartoon of how that works. The idea is that this blue grid here represents space-time, and near the Earth you see that the space-time is not flat, the grid is curved, and that is because the mass of the Earth causes space-time to curve near the Earth. And if we think about some other object, such as the Moon, for example, the Moon is trying to follow the straightest possible path through this curved space-time. And the straightest possible path through a curved space-time is curved, and that's why the Moon follows a curved orbit around the Earth, as do satellites, for example. Now, of course, Einstein's theory is a mathematical theory par excellence. So at the heart of the theory is an equation called the Einstein equation, which tells us how matter causes space-time to curve. And the Einstein equation is an example of what we call a nonlinear equation. This means that the curvature, space-time curvature produced by two objects, is more than just the sum of the curvatures produced by each body separately. This is unlike, for example, an electric field or a magnetic field, where if you have two bodies producing an electric field, the resultant field is just the sum of the fields due to the two bodies separately. That's not the case with gravitation. Einstein's equation is nonlinear, and that makes it rather difficult to solve in practice. So that's why general relativity has acquired the reputation of a difficult theory to work with. Okay, why am I talking about this fellow Einstein when we're in Trinity College? When, of course, our most famous alumnus had his own ideas about gravity, which reigned supreme for hundreds of years. Well, the point is that general relativity is well approximated by Newtonian physics when the gravitational field is weak. What do I mean by weak? I mean that particles falling under the influence of gravity always have speeds much less than the speed of light. Okay, and that's what I mean by a weak gravitational field. Under those circumstances, Newton's ideas are a very good approximation to general relativity. Fortunately, in the solar system, gravity is weak. And so Newton's physics works very well in the solar system. However, general relativity predicts small corrections to the predictions of Newtonian physics. And these predictions have been confirmed to very high accuracy by observations in the solar system over the past 100 years. So there's no doubt that general relativity is a better description of the gravitational interaction than Newton's description. Let me describe some applications. So many of you will use GPS, the Global Positioning System. You use it in a sat-nav, or if you use your mobile phone to navigate. GPS involves a system of satellites in orbit around the Earth, sending signals to and from your sat-nav or mobile phone. For this system to work well, to function correctly, we need very accurate clocks on these satellites, which need to be very accurately synchronized with clocks here on Earth. Now, general relativity predicts that clocks are affected by gravitational fields. In particular, a clock here on the surface of the Earth runs very slightly slower than a clock on a satellite in orbit around the Earth. The effect is very tiny. It's of the order of microseconds per day, but it's there. And if this prediction of general relativity were not taken into account by the software underpinning your GPS system, you would get lost. Okay, so general relativity is important in everyday life. In science, particularly in astronomy, general relativity is very important. So one place where it's used is in the phenomenon of gravitational lensing. So in this picture here, in the center here, you can see this bright object. This is a galaxy. General relativity predicts that light is bent in a gravitational field. And this ring you see around the galaxy is the light coming from a more distant galaxy, which has been distorted by the gravitational field of the galaxy we can see. This is called gravitational lensing, because the gravitational field of this galaxy is acting just like a lens. And in this case, it distorts the light of the more distant galaxy into a ring shape called an Einstein ring. Now, under the right circumstances, this actually lets you do what you can do with a normal lens, which is see further than you would otherwise see. So using this effect, astronomers can see more distant galaxies than would otherwise be possible. It's also used to constrain models of dark matter. So we know that most of the matter in our universe is not the kind of matter that we're made of, it's some other thing called dark matter. And dark matter, by its very nature, is dark. It doesn't emit light, but it does have gravity. So it causes this lensing effect, and so gravitational lensing can be used to search for different kinds of dark matter or distinguish between different theories of dark matter. Okay, so far everything I've said has concerned weak gravitational fields. Let me now turn on to the most interesting predictions of general relativity, which are for strong gravitational fields, and in particular black holes, which is what I work on. So what is a black hole? So by definition, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from that region. So to escape from that region, you'd have to travel faster than light, which is impossible. The boundary of a black hole is a surface called the event horizon. And this is a bit like a one-way membrane. So you can fall across the event horizon into the black hole, but you can't get out again. It's a one-way trip. What happens if you fall into a black hole? Well, general relativity tells us, it says inside the black hole, there's a region where the curvature of space-time becomes infinite. In other words, the gravitational force becomes infinite. And if you end up at the singularity, you'll be essentially ripped apart by gravity. You'll be destroyed. So what would happen if you actually did this? Imagine you have a black hole with say, the same mass as our sun. You can jump into it, but it turns out you can only live a few microseconds after crossing the event horizon before you're ripped apart by these forces. So you don't get to live for very long to experience this extreme gravitational physics. From the outside, general relativity tells us that black holes are very simple objects. They've been described as the simplest macroscopic objects in nature. A black hole in equilibrium is described by just two numbers. Those are its mass and its angular momentum, which describes how much it's rotating. So general relativity certainly admits the possibility of black holes, but in order for them to be relevant, we need a mechanism for actually forming them in nature. The theory, in fact, gives us such a mechanism. It tells us that if we have a star, which is sufficiently massive, more than a few times the mass of our sun, then when that star exhausts all of its nuclear fuel in its core, which is burning hydrogen into helium and then heavier elements, once that fuel has been used up, the star will shrink. It will undergo a process called gravitational collapse. And for a sufficiently massive star, that process will end in the formation of a black hole. So black holes represent the end point of stellar evolution for sufficiently massive stars. And since astronomers tell us there are many sufficiently massive stars out there in the sky, we believe, therefore, that black holes should be quite common in the universe. So this is a theoretical prediction. How do we test it? How do we detect black holes? Well, of course, black holes are black. You can't see them. So the way astronomers look for them is by looking for their gravitational effect on luminous matter. So the black hole causes nearby matter to move in a certain way, and if it moves in a particular way, you can infer properties of the object that's causing them to move. And there are two key properties of black holes which are crucial for this. One is that there is no upper limit on the mass of a black hole. This is unlike a star. You cannot have a star which is more than about 100 times the mass of our sun. It would be unstable. But a black hole can be arbitrarily massive. The second important property of black holes is that they're small. A black hole is very small. If you had a black hole with the same mass as our sun, its radius would be about 3 kilometers. Compare that with the radius of our sun, which is almost 1 million kilometers, much smaller. Perhaps a more striking example is imagine you had some giant planet-crushing machine which you could use to squeeze the Earth so it became denser and denser and denser. And so eventually it will become dense enough that it forms a black hole. How big would that Earth mass black hole be? The answer is about that big. Okay, so a black hole with the mass of the Earth will be about that big. So black holes are very, very small and very massive. And it's this combination of a large mass in a small region which is characteristic of black holes. So here's an example of how this is used. So over the past couple of decades, astronomers have been using very sophisticated imaging techniques to study the center of our galaxy. So in this animation I'm going to show you, this red cross is the center of our galaxy, and these white blobs are stars near the center. And in the top left-hand corner, you can see the date. So if we start the animation, you see the stars follow orbits around the center. And from the shape of these orbits, you can deduce that there's an object located at the red cross there, whose mass is very large. It's about 4 million times the mass of our sun. And from the fact that some of these stars get very close to the center without being ripped apart, we can infer that that large mass is actually contained in rather a small region, smaller than our solar system. And it's this combination of such a large mass in such a small region which really nails this as a black hole. We can't think of anything else which this could be. And other galaxies have central black holes whose mass is even much more larger even than this. There are galaxies whose black holes are up into the billions of solar masses. One thing I should emphasize here is that what we're really testing is the qualitative prediction of general relativity about black holes, that they have a very large mass in a very small region. We're not really at the stage where we're doing precise quantitative tests of general relativity for strong gravitational fields. And that's something that progress is expected on in the next few decades. So precision tests of general relativity for strong gravitational fields are something for the future. Okay. Another important prediction of general relativity, going right back 100 years to the start of the subject, is the existence of gravitational waves. So these are ripples in space-time which propagate along at the speed of light. Much like we can have ripples in electric and magnetic fields propagating at the speed of light. That's called light. Okay, so these are gravitational waves as opposed to light, which is an electromagnetic wave. So how are they produced? They're produced when you have, if you have large masses moving very quickly, you can produce these gravitational waves. And so an interesting, or perhaps the most important candidate for a system that produces these gravitational waves is a binary system consisting of two objects orbiting each other. And those two objects are very compact objects, such as black holes or neutron stars. So a neutron star is a very compact kind of star that's almost as dense as a black hole. So you have two very compact objects orbiting each other. It will produce these gravitational waves. So here's a computer simulation showing that. So these two blobs are two neutron stars orbiting each other, and you can see the gravitational waves propagating outwards as the stars orbit each other. As the system emits gravitational waves, it loses energy, which causes the stars to get closer together until they actually collide and merge, as you see here. And now this new body will eventually undergo gravitational collapse and form a black hole in the center, which we're now going to zoom in on. So there, the two stars have formed this green black hole. Black holes are not really green, they're black. That's a black hole. And this is some of the debris left from the stars, which forms something called an accretion disk around the black holes. But before the merger, we saw these gravitational waves being emitted by this system. Now, so this is a prediction of general relativity. Is it true? Well, these gravitational waves have been detected, but only indirectly. What I mean by that is that astronomers have studied systems of neutron stars, such as this, and they can see electromagnetic radiation, basically light from these stars. And from that, they can deduce properties of the orbit of these stars. And they see that the orbital period, the time it takes to orbit, is changing very, very slowly. And they can measure this change very precisely, and it's in precise agreement with the rate of change you'd expect coming from emission of gravitational waves causing the orbit to lose energy and shrink. And so this is a precision test of general relativity, it's prediction of gravitational waves, but it's only indirect. The waves themselves have not been detected. Nevertheless, a Nobel Prize was awarded for this work. What you should expect to hear about in the near future, the next 5 or 6 years, is a possible direct detection of gravitational waves. So here on Earth. So if a gravitational wave were to come through this tent, now it would have the effect of stretching us in one direction while squashing us in another direction. That sounds uncomfortable, but this effect is absolutely tiny. For the kind of systems I'm talking about, we're talking about very distant systems here. The amount of stretching and squashing would be less than the size of an atomic nucleus, so it's absolutely tiny. But nevertheless, there are experiments going on in the US at the moment which aim to directly detect the effect of these waves, and that's something that they're optimistic they will be able to do in the next 5 to 6 years. One other thing I should say on this subject is this simulation was produced on a supercomputer. It's only within the last 10 years that we've been able to reliably solve the equations of general relativity on supercomputers, and so this has become a very valuable tool in making predictions that will then be compared to observation when these waves are detected. Finally, I should say about these waves is that when we are able to detect them and we're able to use them to look at the universe, it's an entirely new way of looking at the universe. So far, astronomy has been based on electromagnetic waves, different kinds of light. When we're able to detect and understand these gravitational waves, it's an entirely new way of looking at the universe and is likely to reveal many surprises. Okay, my final topic is perhaps, definitely the most speculative part of this talk. So this is a discovery made about 20 years ago. So it concerns theories similar to our theory of particle physics. So particle physics, as explored at the Large Hadron Collider, is described theoretically by a theory called the Standard Model, which is a bit of a boring name for something that describes everything except the gravitational force. So the Standard Model is our theory of particle physics. It was realized some time ago that certain theories which are very similar to this Standard Model, so these are theories of particle physics with no gravity, they're actually equivalent to theories with gravity, but in 4 dimensions of space, rather than the 3 that we live in. So this is called holography because it's similar to the way in which a 2-dimensional hologram encodes a 3-dimensional object. So this is very surprising for various reasons, but perhaps the most prosaic reason this is interesting is that the theories of particle physics which emerge this way are theories in which the particles are strongly interacting with each other. And in particle physics, when things are strongly interacting, it's very hard to calculate anything in the theory, to make predictions. So this holography gives a new way of doing that. You can now calculate, but using 4-dimensional gravity to calculate things in a 3-dimensional theory without gravity. So this has been used, for example, to explain certain results from the Large Hadron Collider. So one of the experiments the Large Hadron Collider has done is to collide together very heavy nuclei to create a state of matter known as the quark-gluon plasma. So this is a very hot plasma of particles interacting with each other, which is very similar to the conditions in the universe less than a second after the Big Bang. So here's a picture of what the decay of that plasma looks like in the Large Hadron Collider. The problem is that, so we have a theoretical description of this plasma in the Standard Model, but because the particles are strongly interacting, we can't use it to calculate very much. It turns out that many properties of this plasma are actually well described by properties of black holes in 4 dimensions using this holographic idea. So this is a very exciting and surprising new application of general relativity. Okay, so I hope I've convinced you that although it's 100 years old, general relativity is still very much at the forefront of modern research with many exciting developments to come. Thank you.
So questions for Harvey now, and I'm serious about the timekeeping of our clock. Because, I mean, I rely on a GPS receiver to compare the time of the clock. But, I mean, is it microseconds?
It's about 40 microseconds per day, the difference in the clock running on the Earth's surface and a GPS satellite.
Oh, that's astonishing. So, questions now. We have lots of questions here. So, one just here. Yes. Hold on, there's a microphone just coming to you.
Harvey, you mentioned that black holes are formed in the final dying of stars, but you mentioned that stars above 100 suns mass are unstable. Mm-hmm. How do you suggest that your black holes of many millions of suns masses form?
Well, that's actually a bit of a mystery. So as I said, many galaxies seem to have these supermassive black holes at their centre, and there seems to be some correlation between the mass of the black hole and the mass of the galaxy that hosts it. So I think people nowadays suspect that the black hole is somehow formed along with the galaxy itself, but actually it's still not completely settled how these really massive black holes are formed at the centre of galaxies. It's a bit of a mystery still.
Oh, thank you. Professor, you gave a remarkable talk, and as far as I could see, without any notes at all, I'm over here.
Yes.
But I have a question. I once heard Professor Wheeler, the American physicist who did some early work on these objects, I heard him on a radio program say, anyway, they're not black holes, they're black spheres. Will you comment? Are they spheres or are they holes?
Well, the surface of a black hole is certainly spherical. It is what it is. You fall into it, you die.
Hello.
I can't see who's speaking. Oh, yes, hello.
I'll just stand up. Hi. I've got a bit of a general question, actually, a bit long. But there's a contrast going between your talk and Barney's talk. And yours was heavily scientific, and Barney's was quite commercial in nature. And my question is, in a rapidly approaching age where people are going to be landing spacecraft on the moon, people are going to be bringing back samples, going to be harvesting resources, and how do we preserve, especially among the young people who are just leaving schools, going to universities, a sense of scientific curiosity of precisely the kind of research that you are talking about, of looking into the origins of the universe and that actually doesn't have an immediate benefit to the world?
Yeah, I think that's a very good question, especially important given that a lot of government funding nowadays is reserved for research which is deemed to have some kind of commercial impact. I would say it's very good that programs like Horizon and Sky at Night continue to cover this curiosity-driven research and bring it to a wider audience. And also some of my colleagues, like Stephen Hawking and Martin Rees and Kip Thorne, have been very good at publicising this work, and their books have sold many copies. And so I think it's important that scientists do this kind of outreach work to continue to bring these exciting discoveries to a wider public. And the public is certainly interested, as shown by the fact that people watch these TV programmes and buy these books. So as long as we continue to make an effort to communicate to the public, I think we should be okay.
I'd also like to thank you very much indeed for a talk that actually helped me understand black holes a bit more. This may be a naive question, but I was fascinated when you said if something goes into a black hole, they're destroyed and they never come out. It's a one-way entry. Mm-hmm. How do you know that?
Well, well, unfortunately, this is something that is a prediction of general relativity, and the only way to test it is to jump into a black hole and die. And once you're dead, you can't really. Yes, yes. Unfortunately, that's the nature of black holes. So all we can test is whether general relativity predicts accurately what happens outside a black hole, and then we'll just have to take it on trust that it covers the inside as well.
Eddie Redmayne told us that the black holes will be... Oh, sorry,
I can't see who's speaking.
My name's Andrew Senior,
yes,
sorry.
Yes, hello.
Eddie Redmayne in the wonderful film, you mentioned the guy's name, Hawking, I think.
Yes,
that chap.
Yes.
Told us that... wrong college. Told us that black holes emit radiation and evaporate. And yet we have supergiant black holes. Mm-hmm. So they must be accreting.
Yes.
So can we not see... How do we square that?
So this is the famous Hawking effect. So I didn't mention this at all in my talk because this is an effect of quantum theory. So general relativity does not take quantum theory into account. It's what's called a classical theory, which means non-quantum. But Stephen Hawking famously showed in the early 70s that when you take account of the laws of quantum mechanics, black holes are not completely black. They actually emit this radiation. But it's an incredibly tiny effect. If you have a black hole with the same mass as our sun, then it would be emitting radiation at the same rate as a hot object whose temperature is of the order of billionths of a degree above absolute zero. And a supermassive black hole will be even colder. So from the astrophysical point of view, this effect is totally negligible. And it's only important really for thought experiments involving attempts to apply quantum mechanics to the gravitational field itself. So it's seen as a major discovery on the road to going beyond general relativity and inventing a quantum description of the gravitational field. But from the practical point of view, at least as far as astrophysics is concerned, it's not important for solar mass, or certainly not for supermassive black holes. The only black holes to which it would be important would be if you had a very tiny black hole. So if you had a black hole with the same mass as a mountain, that would actually be a very hot object because of the Hawking effect. But actually there's no evidence at all for the existence of such tiny black holes. And so as far as we're aware, it's not important astrophysically.
Could I ask a very simple question? Into what did the Big Bang explode, and into what is the universe expanding?
Well, the stock answer to that is nothing and nothing. The general relativity predicts that space and time themselves came into existence at the instant of the Big Bang, and so the universe isn't expanding into anything; it's just expanding. It's hard to visualize, but that's the picture.
You mentioned dark matter in your talk.
Sorry, I can't see who's talking. Oh, yes, okay.
You mentioned dark matter. Do you think it'll be found in the LHC? And if not, do you think it is in fact just the new ether?
No, I think there are good reasons to believe that dark matter is just a new kind of particle. I mean, particle physicists have no trouble inventing theories which contain particles that have all the properties of dark matter. They're also quite good at explaining why they wouldn't be observed at the LHC if the LHC doesn't observe such a particle. So there's quite a lot of freedom in how one constructs a model of dark matter. And so, but it would be very exciting if the LHC does discover a dark matter candidate, because that would obviously confirm the existence of this particle. I think speculations that somehow general relativity is wrong, and that's the explanation for why we need dark. Well, general relativity is wrong, and therefore we don't need dark matter. We just need to change the laws of gravity. I think that's very unlikely. Yeah.
Harvey, hello, Andrew.
Who am I looking at? Yes, hello.
Barney's going to commercialise space travel. How long before you can commercialise time travel, please?
Well, have you seen this movie Interstellar? That probably made quite a lot of money, didn't it? So there's commercial time travel. It's maybe some of the physics in it wasn't entirely realistic, but yeah. As far as we're aware, time travel is not possible.
Harvey?
Yeah.
Robert Edison. I can't get my head round infinity. Now, if the universe is expanding, as you've just told us, into nothing, does that imply that the universe is infinite? And therefore non-definable?
Not necessarily. I mean, this is always something that's very hard to explain, but the standard analogy people give is imagine that the surface of a balloon. Right? Imagine that is the universe, and you're an ant living on the surface of the balloon. You're a two-dimensional object. You're not aware of the dimension transverse to you. Okay, so you can inflate the balloon. The surface just expands. From the point of view of an ant on the surface, it's just expanding. It's not expanding into anything. It's just expansion. And in some sense, it's a bit like that. But ultimately, the mathematics make sense without having to be able to visualize it, I think is the way I'd say it.
Thank you very much. That's a great way to end our morning. We can expand into the drinks area.